Manvin, Richa, Rishikesh. Thank you. So in today's lecture, we just have to understand the objective function of our generator adversarial network. And we all understand that how this network is actually working is that you have got some data points. This is normally distributed. These are going to be normally distributed. Given this normally distributed Z, we are sampling from this distribution certain points. And when I take these certain points or these vectors and send it to my generator network, which is a network that can convert axes ZZs to different axes, upsampling network, you're going to get a Z, which is you're going to get a GZ, which is actually a type of image that you are having. Given these images, you actually try to somehow see that they are going to follow a distribution, and that distribution is actually the GZ distribution, probability of GZ. That's a distribution that's actually following. And this is the distribution of our real data. All these images are actually real images. All these images are actually the generated images, and we wanted our network to be trained in such a way, this G, so that whatever it actually generates, it's very close to the things which are actually coming from the real distribution. And in order to do that, what we have done is that we take things. Please mute your mic. Please take and mute your mic. Yeah. So it goes here, and so instead of how to manage that this distribution become equal to that distribution, we train it using a discriminator, which essentially tries to see that the images which are generated and images which are coming from my data set, both of them are actually two different type of images. And discriminator started to understand that what's the real and what is there in the real things which are distinctive than this fake distribution. And distributor started to understand that why this what are those features by which this real data is actually real data. And once he started to understand that, we just wanted to somehow find out a way by which we let this generator understand that these are the important things that you will have to generate, and have those features in your image, so that your discriminator started to behave that whatever you are making, that's actually very close to my the real data. So in this way, this is one network, this is another network, and both of these networks are being trained in such a way so as to play a specific game, that's the adversarial game. And the job of the generator is to fool the discriminator, and the job of the discriminator is to judge the generator. So if generator is able to fool this discriminator by its own generated things, then discriminator will not be able to judge the things. And if it's not able to judge the thing, which essentially mean that if it is coming from real distribution, it may say that it is coming from it's coming from fake distribution, or if it's coming from fake distribution, it may say that it's coming from real distribution. And this judgment is actually going to be a binary classification or the binary judgment, which essentially mean that this discriminator becomes no better than a random coin toss. So you do not know anything about the what is real, what is fake. So instead of doing any classification, you just started to do some random coin toss, and with a 0.5 probability you are correct. The discriminator D and the generator G networks are trained alternatively. Yes, they are being trained one by one after other. First discriminator is trained, and then generator is trained, while keeping the other one fixed, which essentially means that yes, you have a network G, you have a network D. I have got a loss. I take this log, back propagate this. I will take this loss 1 minus that of loss and probably back propagate here. So once generator is trained, then discriminator is trained, then generator is trained, and then you have got new lot. You see those images, it will go again, it will go here again, you will get the loss, then you will train this, and then you will train that. Loss function is very straightforward here, that this is my binary cross entropy loss, where y and y hat, this is my predicted level, this is my ground truth. And binary cross entropy says that y log y hat 1 minus y log of 1 minus y. hat. Why I have written it is that your discriminator, first of all, we are going to write the loss for the discriminator function, in which either you are going to show it as an x or you are going to show it as a gz. So if it has seen x or it's going to see a gz, depending upon that, the output is going to be dx or d of gz. And the corresponding ground truth is actually 1 or it is 0, depending upon if it is coming from the real, the ground truth have to be 1. If it is coming from fake, the ground truth should have to be equal to 0. So so the point is that if I take a loss, here it is y hat, here it is y. So let us see what's my y. So y hat is this and y is this. So if you have seen x, then dx is actually y hat and 1 is actually the ground truth. And this value, what we wanted to do is that this value should have to be maximized. This value should have to be maximized. So if you want to do maximize, so it's I have shown you that this is actually the true things. So it's trying to, you know, somehow maximize this thing, that whenever I see dx, I has to say that it's 1. So the loss between them, between this and this, so it's going to be that this value should have to be, you know, as close as possible to this 1. So we wanted to somehow maximize this value, which essentially mean that the dx value is going to be maximized, log of dx is going to be also maximized. Similarly, d of g of z, which is actually here. So here, so what's going to happen over here is that this is my y hat and this is my 0. Both of them are coming over here. So this, and the value is going to be, so I wanted to somehow make sure that d need to somehow minimize d of this thing, because this value should have to be as low as possible or as close as possible to 0. So if you wanted to minimize this, then log of this can be minimized and 1 minus of that is going to be maximized. So 1 minus that is actually going to be maximized. So this is maximizing, this is maximizing. If I'm maximizing both of these things, just you take one single sample. Right now I'm only talking about one sample. If you have, and you show it to your generator, and then you show it to your discriminator, and then you have got a loss, and according to that loss, what you need, what your discriminator need to do, your discriminator need to say that whatever I have generated, this dx, log of that plus log of 1 minus d of g of z, the addition of both of these things should have to be maximized for given d. So given this d, if I make these are two different graphs, graph number 1 and graph number 2, what is happening over here? In this direction, this is d of x. In this direction, this is d of g of z, d of x and d of g of z. And this axis is actually log of dx and log of 1 minus d of z. So what we just try to show is that there is a log relationship, as you all understand, and here this is a log relationship, and here is 1 minus log of 1 minus x. 1 minus x, that's actually the plot that's happening over here. You all can understand that log graph is actually going like this, and 1 minus log of that is going to be something like this. This value is actually 1. This value is 1. This value is also 1. And what you can see here clearly is, yes, that what is going to happen is that this graph is actually moving towards this side, and this graph is moving towards this side. What does it mean? It actually means that I am trying to take things wherever it's actually starting from here. Initially it's starting from here, this graph, and actually trying to reach up to 1. One thing one should have to understand, that dx is actually a probability, and the value between 0 and 1, only those things are meaningful. Anything which is outside this is not meaningful. So that's why I just have crossed that these values are not meaningful. Similarly, these values are also not meaningful, because they are not the probabilities. Probability has to be between 0 and 1. This is first thing. Second, that if I see log of dx graph, this is actually initially starting from this point and keep on moving, and we train it in such a way so that from where you are starting, you need to come up here. Why? Because log of dx should have to be as close as possible to 1. these things need to be reaching or approaching towards 1. What is happening over here? Here what has happened is that you are actually looking some real images and giving a very small probability. You are looking a very some real images you are looking, and you can say that the probability is very low. And now you see that when your network is training, soon it understands that these are real, these are real, these are real, and at some point of time it has to reach and give these real values or the real images the probability 1. Similarly, what is happening over here, that you are looking certain images which are really fake, and you are giving them a very high value. So fake things are getting high value here, and slowly at some point of time your network started to understand that these are the fake images. It has to be somehow take it to this point. And these are the points where it can actually started to converge. This was for the single sample. And if I say that you are going to have a batch, which essentially mean that in a batch you are having, I just have shown that you are having x's or you are having d of g of z's. So d of g of z's. So if you have got a batch in which you are having multiple such images, your discriminator is going to see all of them. And what it has to do is that that for all of them it's going to do an aggregation. So for all of them, what is the total loss that you are going to have? That is actually the expected value, that whenever I take any x which is being sampled from the real data. Please mute your mic. So if it is coming, if your x is actually coming from a real data, that's why I've said that the p data is actually the distribution of my real data. So your x is actually coming from the real data over all of those x's. If I choose something for within a batch, that's why I'm saying that this expectation is only within a particular batch. So in a batch, I have chosen certain samples which are coming from the real data. Over all of them, you take the log of d of x and see that what is the average value that you are getting. Same thing is happening that if you have chosen certain z's with certain probability distribution, that is actually a unit normal distribution, you take them and show it to your generator, and the images that you have got after generator show it to your discriminator, and 1 minus of that and the log of that value should have to be maximized so that this is minimized, so that this becomes, so that this go as close as possible to 0, so that this thing becomes as, poor as possible with respect to your axis. That is the objective of your discriminator. If this is the objective of your discriminator, I hope that this loss function is just clear. We just have seen that this value and this value, why they are coming and why these expectations are coming, because now we are working over the not only over a single image, but we are now working over a complete batch of images. Now
Sir,
what happened? Yes.
sir, a basic doubt, sir. This d of x and d of g of x both are scalars, right?
No. Okay. Yes. They are scalars. Yes.
Sir, so you mentioned they are distribution before. So
No. My only point is that, yeah, so this x is coming from a distribution, this z is coming from a distribution, this gz is following a distribution, and this dx is actually the output of my discriminator.
Right.
And this is also the output of my discriminator when I have shown it a generated image.
Right. So they are scalars.
They are scalars. If I have said anything like that, probably it may be some wrong thing.
Okay, sir.
dx and dx or whatever d, this function is actually a discriminator function. It will take an image and going to give you a value between 0 and 1. If it is close to 1, it is real. If it is close to 0, it is fake.
Right. Okay, sir.
Okay. So one discriminator is saying this. I mean, this is the loss function for my discriminator over a batch. What is going to be the loss function of my generator? The generator need to fool the discriminator by generating images as real as possible. Hence, if you take any real sample, if you take any fake sample, or you just sample some z's from unit normal distribution, show it to my generator, then show it to my discriminator. Then this value should have to be as low as possible that D is actually looking for. But if you take this Z, show it to my G, and then show it to my D, what is the expectation of a generator? Generator need to make it as GZ has to be as neat and clean as possible with respect to any real images. So what is going to happen is that this thing, discriminator wanted to make it 0 and generator wanted to make it 1. That is why if you wanted to maximize this, then 1 minus that should have to be minimized. Is this okay to everyone? Wait, I will again take a question. We are here that this is going to be the loss function for my generator. This is going to be the generator, and let us see it once again that what's happening. I have got a generator which is going to take some Z and a theta1, some parameters of that. My discriminator which is going to take some axis, maybe coming from here or maybe coming from here. Now do not confuse between that only axis can come from here. I just have written this as a variable that this x can actually be here or here, maybe dependent upon some theta2. And I just sample a point from here, show it to my network, which is being parameterized over theta1. It is going to generate GZ for me, which is going to follow a distribution that is, we are saying that PG distribution. This is the PZ distribution. That's the unit normal distribution. This is the distribution for my generated data. And this is the distribution that I'm saying that the P data distribution. And I'm assuming that this is my P data distribution, that my data is actually somehow following. I wanted to estimate this distribution via this distribution because we are only learning this distribution. So the label which is actually given to the guys which are coming from the top part is actually 1, and the lower part they are actually label 0. So yeah, so showing the generator loss again in a very simple way. Same thing I'm going to show it to you. Please do not get confused. The same thing is again being written. Input is GZ, output is going to be D of G of Z of my discriminator, and the corresponding ground truth has to be equal to 0. So D of G of Z 0. This is the thing, that's the binary cross entropy loss, which can actually be seen as the log of this and the expected value of this. Yeah, so just for the sake of completeness, what we are writing is that, remember one thing which is very subtle and one should have to understand, that G is never going to, this generator is never going to got an access to this data. It's never ever going to see this real data. So G is never have got a access to us to see a real data at all, because it can only see a Z, and Z is being sampled over here. So it do not have any idea that what type of real distribution is. It's only going to see that via the losses which are actually being back propagated from 1 minus that of that generator, if I say, sorry, discriminator. So what I wanted to say here is that since G is never going to see any real data, just for the sake of completeness, because this was actually loss of my generator. Here you can see only G's are being, it's only Z's are being there. Only Z is available. I just have written the same thing which was actually being written over here. Actually, I forget. If I request all of you to please take your pen and pencil. If you have your copy and pen, because huge amount of math is going to come and multiple steps are there. Please take out your pen and your copy. And as soon as you are done, please write in your chat that you have got your pen and pencil. No, it's audible. It's well audible. What happened in between? Yes, sir. Okay, sir. Am I the only one? Oh, Rohit Damu was not able to listen. Probably it was with him. And what I was trying to say was that, yes, please take your pen and a copy and pen and write in your chat that you are ready with your pen and copy. I'm waiting. Ready. Ashima, Divyansh, Thakur. Only 2. 3, 4. Please get ready. We need to do this, otherwise we will not be able to understand. It's not going to be easy stuff today. Ready? Ananya is ready. Chat. Yes, yes, sir. Yes, sir. Aditya is ready. Chandresh is ready. Toshendra is ready. Yes. Anurag Pandey is ready. Good, 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 good. Get yourself ready as fast as possible. Yes, ready. I assume that most of you are ready. Once we understand this, first you write this stuff. First, you all have to write this whole thing over the batch. Keep on writing it again multiple times. Don't worry. Whatever I am saying, that please follow. At the end of the session, magically you will be able to understand each and everything. Otherwise, you will only be able to understand the crux. Right now, I'm trying to cover the whole thing, so you will be able to understand each and everything. Max of D, expectation of X is coming from the real distribution, real data distribution. Log of D of X plus expectation of Z coming from PZ, log of 1 minus D of G of Z. I hope that this is done. This is for my discriminator. Now what generator is going to do? Generator is taking this stuff and minimizing this. Because discriminator is maximizing, as a generator, I need to minimize. You should not be in a position to understand that it's being made by me. So you are maximizing, I am minimizing. So I'm going to minimize this stuff. Once I've said this thing, the next thing that I wanted you to write is write down this stuff. What's the work of my generator? And the work of my generator is to minimize this. Along with that, I just have added this one more stuff. This was the thing which was anyways being there. It was minimizing this. I am minimizing this plus another stuff this. But do not worry about this thing. And the reason, you please write this thing as well. That's exactly this thing that is the exact thing that discriminator is maximizing. This was the thing generator need to minimize. Along with that, I have added one stuff, but you need not to worry about, because it is just that whatever along with this, you write A, B, C, D or whatever the thing. If you wanted to minimize, this thing is anyways not going to be shown to my generator at all. So you can write this thing as well. I will tell you that why I have written. That's just for the completeness. Then minimizing G, this whole thing. And now it's going to be the complete loss function, which is that V, that's going to be my loss, and D is my discriminator, G is my generator. And now you see that it's not going to be a single step optimization function, because you are having two different networks. They are going to be optimized for two different tasks and two different loss functions. We somehow managed to make it in such a way that the loss function of both of them becomes exactly equal. That's why we just have added. But one is maximizing, discriminator is maximizing, and generator is minimizing. That's why it's going to be a min max loss, max and min loss for discriminator and generator. And what is happening over here, that log of D of X has to be as high as possible for discriminator, because it's coming from real data, and discriminator has to say that, oh, it has to be 1. And discriminator has to show, oh, it has to be 0. So if it has to be 0, then one of that has to be somehow maximized. So this is going to be maximized, and minimization step is going to happen for the generator. It will say that, oh, this value has to be random vectors got converted into a really good image, so that discriminator has to say it 1. So this thing has to be minimized by G. Now wait over here, and let us take if there are any questions that you have written. Please write it down, and if you have any question, then you can ask. Yes, I assume that most of you actually have understood. And then this was actually the paper, maybe in 10th of June or something like that in 2014. Goodfellow has written this paper, Generative Adversarial Network, GAN. There it was their first paper. on GAN. Probably they may have written certain thing more, but this was the most major impactful work that they have at that point of time published. And the mini stochastic gradient descent training algorithm for the generative adversarial networks, what it is going to do is that you take a sample mini batch. We'll make a small sample mini batch, Z1, Z2, Z3, Z4, and M such things from a prior distribution. And then you take them and show it to me, show it to my, and then you take a mini sample from real data, P data. So you take PGs, you take P datas, and so this is my, sampled noise, and these are my sampled real data. If I show my generator these noise vectors, they are going to generate images for me. What are they? This is going to be for all of my Z1, Z2, Z3, Z4, I show them one by one within my one mini batch. I am going to get M such images, show it to my discriminator, 1 minus of that's going to be the log. Similarly, I take images like this from my real distribution, whatever the M images that I have chosen, shown it to my discriminator, log of that, and add it to 1 to M such things. So you in a batch you are having 2 M things. 1 M is coming from this, other M's are actually coming from them, and it's going to be 1 by M. And yeah, so that's this has been panel. So you differentiated with respect to the parameters of your discriminator. So take this loss and differentiate with respect to the parameters of your discriminator, and your generator is going to be in such a way so that whatever the sample. So now once you have got this thing, you you take M samples, Z1, Z2, Z3, and Zm chosen from this, show it to your generator, get a discriminator, find out this value. So essentially this is only this much value, and you add it and differentiate it with respect to the parameters of your generator. So there is only one catch. Probably if you ask, then I will tell. If you have any questions about this, then you please ask about this mini batch stochastic algorithm.
Sir, in the equation that you've shown,
Yes. Yes.
Yeah, sorry.
आप क्वेश्चन तुरंत अपना पूछ लीजिए ना.
So there is some echo actually.
इको हो रहा है, मुझे समझ में आ रहा है, इसीलिए बिना रुके पूरा सवाल एक ही झटके में बोल जाओ.
अच्छा सर, जो आपने इक्वेशन दिखाया था जनरेटर के लॉस फंक्शन में, उसमें हमने dx, the first term was dx, but पेपर में हमने वहाँ dx नहीं दिखाया है. That is one thing.
फर्स्ट टर्म वो dx है ना?
नहीं सर, नीचे जो
ये जनरेटर का है ना. हाँ, ओके. That is just to write in the single form. मतलब वो हमने ना complete form में लिखने के लिए दिखाया था. मैंने बताया था ना, इस वैल्यू के ऊपर तो वो डिपेंड करता नहीं है. So, ये जब इसको देखना ही नहीं है तो कोई फर्क नहीं पड़ता इसके लिए. अंडरस्टूड?
ओके.
तो जनरेटर के लिए सिर्फ इतना ही है जो कि यहाँ से निकल के आ रहा है, और डिस्क्रिमिनेटर के लिए पूरा है.
एंड सर, इससे लग रहा है कि जब जनरेटर ट्रेन करेंगे तो उसके पैरामीटर हम मॉडिफाई करेंगे, और डिस्क्रिमिनेटर में फिर डिस्क्रिमिनेटर नेटवर्क के करेंगे, थीटा डी एंड थीटा जी.
इसीलिए इस चीज को डिफरेंशिएट किया, इस चीज को पूरा डिफरेंशिएट किया थीटा डी के रिस्पेक्ट में, और इसको डिफरेंशिएट किया थीटा जी के रिस्पेक्ट में.
हेलो सर.
हाँ पूछिए.
सर इसमें ऐसा, मतलब इस एल्गो में भी तो ऐसा हो रहा है कि डिस्क्रिमिनेटर जो है वो ज्यादा बार ट्रेन हो रहा है, और जनरेटर मतलब एक ही बार ट्रेन होगा, अपन देखें अगर इस एल्गो से तो.
हाँ ठीक है. ये इन्होंने दिखा रखा है कि एक के स्टेप्स के लिए इन्होंने चलाया, और उस के स्टेप के बाद इसको एक बार कर रहे हैं. ठीक है.
हाँ तो बट सर आपने कहा था कि अगर ऐसा अपन ऐसा करते कि डिस्क्रिमिनेटर बहुत जल्दी सीखता है, तो
हाँ
अपन जनरेटर को ज़्यादा सिखाते हैं और डिस्क्रिमिनेटर को मतलब थोड़ा थोड़ा सिखाते हैं,
हाँ।
बट
नहीं यार,
इसमें तो
के तो
उल्टा।
इन्होंने लिखा ही हुआ है, 1 है वो, मतलब बहुत सारा डिटेल है, समझे ना। ये बहुत सारे टास्क पे डिपेंड करता है कि अब अगर तुम्हारा जो बनाने की चीज है इट्स वेरी वेरी सिंपल, मतलब इट डिपेंड्स कि जनरेशन टास्क इज इजी और डिस्क्रिमिनेशन टास्क इज इजी, ठीक है। तो
ओके
इस वाले केस में इन्होंने के इक्वल टू 1 रखा है, बट इन मोस्ट ऑफ द केसेस इट हैज एक्चुअली बीन सीन, you all can understand that if I started to come up with more and more complex distribution of my data, real data, then generation becomes more and more difficult. तो फिर मुझे कई बार बराबर बराबर ट्रेन करना पड़ता है, कई बार इसको ज्यादा ट्रेन करना पड़ता है, कई बार उसको ज्यादा ट्रेन करना पड़ता है। हमने अपने कामों में जब ट्रेन किया, what we have seen is that most of the time we need to train generator more and discriminator less, otherwise very soon discriminator becomes very good. Anyone
sir.
else? Okay, anyone else? ठीक है, आगे बढ़ते हैं। तो यहाँ पर एक ही बात बस सिर्फ दिखानी थी मुझे कि that is here it is ascending, here it is descending, because here you are maximizing and here you are minimizing, so that is the only thing. ठीक है, now going on to some core stuff, and again your copy and pen is going to be very very important for you, because what is happening over here we all understand, and how we can train a GAN in such a way that is good for us, and we understand that there are two types of losses, loss number 1 and the loss number 2, and both of these losses are being used specifically to train discriminator and generator in the respective ways. But why, if we trained in such a way, they are going to learn the distribution of this PG, the generated images, this is actually going to be close toward the P data distribution. Now this is something which is right now not very intuitive, at least in terms of mathematical understanding, but theoretically you can understand that discriminator is somehow trying to figure out that how to differentiate between the real and the fake images. And the places where it is able to do that successfully, those things are actually being used and fed back to my generator, that okay, see, you are generating some things like this, but your discriminator is actually looking for much more complex features. So this is not being directly fed, but is being back propagated in terms of losses. So this is going to happen, and if this happens, generator becomes smart in some senses in some point of time, so that it started to understand what to show eventually to a deep neural discriminator network, so as to come up with the classification label as close as 1, because the whole requirement of a generator is to generate things which can get a label of 1 or as high as possible label from a discriminator. So this is the thing that's incorporated inside such an adversarial training, and assuming that this is going to somehow optimize in such a way so that we started to get the best possible or our data distribution and our generated distribution comes as close as possible. Now let us prove few things what they have shown. Point number 1, that first we will show, please keep on writing now, and equations you can write. If you wanted to write the statements, you can also write those statements, but equations that you are going to write, they are going to be very very important for you. We need to show that given any fixed generator, I fix my generator. Now you can see that they are being trained alternatively. This is also called as alternative maximization minimization, because if you have two objective functions, then how to optimize both of them simultaneously. So this is the alteration, maximization and minimization. So first you maximize and then you fix that, and then with respect to that fixed version you minimize. You have one thing, you have second thing, you fix it and then maximize it, and then you fix it and then minimize it. So this is called as the alteration strategy. So what we are going to show here is that first we will show that given any fixed generator, if I fix my generator, now generator is not being trained. I'm not anyways back propagating this thing. For that step, your generator is fixed and your generator is generating the same. I mean, if you show one X or any Z, it's going to give you some Z, some G of Z. So right now it is fixed for this case. And optimally, we wanted to achieve the optimal D hashed. Now, what is the meaning of the such optimal discriminator? This is the asterisk means that optimal, D means discriminator, and G means the given fixed, for a given fixed G. So for a given fixed generator, I wanted to come up with the optimal discriminator. What is the definition of such an optimal discriminator? The optimal discriminator's definition is that this is going to be my loss function in which I am having a D and I am having a G. My G is actually fixed right now. Out of all possible Ds, there are going to be infinitely many, all possible Ds. What is the best possible D for me? And that is going to be this thing. What is the best possible D means that if it see anything coming from this G, it is going to say that this is fake. That is the best possible D for you. So all possible Ds which are being there, I wanted to choose the one which is giving me the best in terms of losses with respect to my G. And it's being shown, we are going to prove that it's going to be shown that such an optimal discriminator for a given G is actually going to be P data divided by P data plus PG. What is P data? P data is my real data distribution. What is my PG? PG is going to be my PG is going to be my generated distribution. This is the thing that we need to prove. I just have written that that's my point number one, that what we wanted to do. Okay. And now you can understand that if that is your best possible D, then, you know, given this fixed G, you need to come up with the loss, and that's whatever the loss that you are going to get, given this fixed G, whatever the images that you are going to get, the loss has to be minimum. So you take this G, generate all possible images that you can generate. It's actually a theoretical stuff. You take this G, generate all possible, you know, images that you can, and show it to all possible Gs, all possible Ds. Out of that, this D is giving me the best performance. That is the D that we are actually looking for. And it is being proved that it's going to be equal to something like this. What's my second point? My second point is that now given a fixed best possible optimal generic discriminator, how can I get the best G? To get the best discriminator for any given, say the best optimal, say the best discriminator. I have got the best discriminator. With respect to that best discriminator, how can I get the best generator? What does it mean? This means that right now my DG is going to be fixed, and it's not even going to be fixed. It's going to be my previous time best optimal generator. If you choose that best optimal fixed, at every step, if you take a G and fix it whatever and find out the best one, and then you fix it, and this best one, if you choose, if your optimization is going in the best direction, you are every time choosing the best one. If you choose that best, if you can get this G, what that G is going to be, what that best G that you are going to get. So it is going to say that again, if you have chosen this best, what is the next best G with respect to this that you can somehow estimate, and that is the argmin for all the G's which are possible, for all the G's. with respect to this discriminator, what, suppose that this G is the one which is most of the time being able to fool this guy. So I wanted to find out that G that is going to be, and that is why it is argument. And if you say that that is my G asterisk, which is being defined like this, what's being shown? It's being shown that this optimization, if you are going to do, it is going to have a unique solution, and it's being achieved when your P data and your PG is going to be equal. You see that now the thing is coming, that this optimization is only going to happen and is going to achieve a unique solution when both of these distributions are going to be as close as possible. And the second thing is also going to be shown, that minimizing this is equivalent to minimize the JSD between both of them. Now I guess that you all understand that what we are heading towards. We are heading towards a theoretical justification that that this alteration, maximization, minimization, which will say that if you fix G, I'm going to give you a D, which is the best possible. If you choose that D, and if you choose that D and come up with the best G, this minimization is actually equivalent to the JSD minimization between P data and PG. This is the thing that we are going to show. If you have any question, then you can ask. Anushka, do you want to ask anything?
No, sir.
No, sir. Good. I assume that it's not very complex, whatever I have shown till now. Other things are also not going to be very complex, but only thing is that certain things, several things are actually being written. So I tried to explain it in the best possible way. Please keep on writing the stuff. Let's prove the first point. For any given generator, I'm fixing a generator, I'm giving you a generator G, and our objective is to get the optimal D. Yes. So D asterisk is going to be V. For all D's, I wanted to get the best possible D for a given G. D asterisk is going to be, what's your V, what was your objective function? My objective function was, this is the X. So now I have got a expected value. You all understand that is for a batch. For a given batch, whatever I have accumulated from my real data, I show it to my discriminator, and log of that, this value has to be maximized. Similarly, whatever I have generated, shown it to my discriminator, 1 minus of that value should have to be maximized. Basically, this value should have to be minimized. I add both of them. And maximize it. That is your discriminator loss function value. This is straightforward. Please keep on writing this stuff, that this is my X. This is the same thing again being written, discriminator loss function. Now, what is the meaning of the expectation? You all understand that if I give you a variable X, and it's actually a random variable. This is a random variable X, which is actually having a distribution probability of X. Then what is the average height? Or suppose that X is the height of a community. Height is going to be the height of the community, whatever the samples that you have, X. And if I do it in this way, then it is going to say that what is, and height of a community is, height is going to be between 0 and 7 feet. And some of you may agree that 0 to 7 feet, it's going to be most of the time something like this, because most of them us are going to be between 4 to 6, in between 5. Most of us are actually going to have a distribution like this. So that is the distribution, and this distribution is this distribution. That's the distribution I'm talking about. And X is a random variable, which will say that if I take any person and take his height, then what is going to be his height? That's a random experiment, output of a random experiment, which is actually following a distribution. So what is the expected or an average height? Average height is going to be for all the X's or the heights that you are going to see, and with what probability you are going to see that height. You multiply and dx, that is going to be the expected value of a random variable following a probability density function Px. That's the straightforward definition of any random variable. Then again we write that Vg of d, which is actually equal to this plus this. You divide it into two parts. First part is actually A and the second part is B. This whole thing is going to be optimized for discriminator, and this thing is going to be only optimized for the generator. But for the discriminator, we are having A part and we are having B part. Both of these parts are there. Keep on writing. You write this function again. Please don't hesitate to write it multiple times. VGD is this distribution multiplied by this. And okay, so why we have got this thing? I assume that you all can understand that previously it was written like this, that the expectation X is coming from this. And if I say that the expectation, this is the definition for this, in which this probability of X to X, this has to be multiplied. That is why I have multiplied this value. That is why I have multiplied this value. Right. So your X's are actually coming from the distribution and your Z's are actually coming from the Z distribution. That is why they are being multiplied by them and integrated for all the X's and for all the Z's. So that's actually the continuous variation of your expected or the discrete expectations. Right. So I assume that again we have written the same step again. Random variable transformation. Now stop over here and moving towards another concept that's being required. So first I'm going to show that, and then we are going to use it over B part, not over A part. A part remains to be the same. B part is somehow going to have a type of transformation. So here you can see that everything is in Z. Here everything is in X. So that is why we are having two different integrals. Is there a way by which I can convert my Z variable into some X or some other variable? In integral, you all know that I can transform my variable from one to another. If you have some X squared something, if I place X is equal to, root X, then it's going to be X power 4. Or sometimes you have to place that X is equal to sec square theta or cot square theta or something, and things started to work. Similarly, here what we want to say is that can I convert my Z or transform my Z into some other variable? For that, we need to somehow understand the random variable transformation. So this is orthogonal to whatever, or not orthogonal, I will say that not too much related to whatever we have done till now. It is just one formula that I'm going to use. So that is the thing that I'm going to show in front of you. I have got a X random variable. It is going into a transformation. A G transformation is happening over here. Some function is there. I take a random variable, pass it to a function, some G function to me. I know this function and it's an invertible function. I will get a Y random variable. I've got a X random variable. After transformation, GZ become a Y random variable. This random variable's distribution was known to me. Can you tell me that after transformation, what is going to be the distribution of my Y random variable? So we are assuming the invertibility, which essentially means that X is equal to G inverse of Y. X is equal to G inverse of Y. From here you are getting. So how to get this distribution in terms of this distribution? This distribution in terms of this, we are not going to prove this. It's very easy. You can see multiple books that a distribution of Y is going to be equal to the derivative of X with respect to Y multiplied by the probability distribution of X being fed to this X. You just have to see that what has happened. Why it has happened, for that you can see certain books in which it's being actually proved. What you are doing is that I have X random variable, I have Y random variable. Y is a random variable which is actually being a transformed version of this X transformed via G. I know the distribution of this X. I wanted to know that, can you tell me the distribution that I am going to have of this transformed random variable, which is being defined as dy by dy of G inverse Y and probability of X being fed by G inverse of Y. This is the thing, and this is actually a thing that we are going to use. Now let us see, first of all, in the case of our GAN, what is happening, that I have a Z variable which is being fed into my G variable. Z moved into a G variable. I am going to get a X variable. Again, it's actually a random variable. X is again a random variable, which is going to be equal to G of Z. This Z is following Z distribution. Can you tell me that what is the distribution this guy is going to follow? I assume that now you all can understand. X is actually going to follow a distribution that is the distribution followed by the generated image, because this is being coming from a random variable, random distribution, unit normal distribution. G has converted into some X. I wanted to know that what is the distribution this X is going to follow when my Z is equal to G inverse of X. So we are assuming that whatever we are doing over here, it's invertible. And if it's invertible, then you can have a, a image, and from this image can be have a Z, so you can train such networks as well. So using this stuff, can you estimate what is going to be PG? Yes, my PG X is going to be, my Z is G inverse of X. So now you can see that PZ G inverse of X d by dx of G inverse Y. So that's actually X over here. This is what we are going to do. I request all of you to keep on writing it again and again, because there is nothing more to explain. You just have to do it via your hands and apply your mind in between. It is just that this formula, what we have applied, I have got Z, I have got X, I have got this distribution. I wanted to know this distribution. I just have applied the above formula. PG is going to be the G inverse X differential multiplied by G inverse of X being fed to the actual source distribution. And once you do that, PG is actually equal to this. Now what you can see here, that when my PG becomes this, now again coming back, why we have done this, again coming back, because I have said that we have got A, we have got B, here only X value is there, here only Z value is there. Now you see that here only X value is there, only Z value is there. Now I am taking this beta, and instead of, I'm going to do a transformation. So let us do it in this way, that my second term, my B term, is the integral of probability of Z log dgz dz. I hope that is again clear. I just have rewritten the whole thing completely over here. Is this okay to everyone? I assume that it's going well. If you have any question in between, you can ask, but I'm sure that's very, very simple mathematics which is happening right now. You just have to keep on writing the stuff. I'm sure that you will be able to understand, because there is nothing much more complex which is happening. I just have written things over here. Z, PZ, log of 1 minus dz, Z. What I wanted to do is that I'm changing the variable from Z is equal to G inverse of X. Z is equal to G inverse of X. Therefore, dz is equal to its derivative multiplied by dx. So its derivative is actually this, and multiplied by dx. I assume that we all can understand this thing. And if I say that Z is equal to G inverse of X, why we have done that? Because X is actually equal to GZ. So your Z is equal to G inverse of Z. So our claim was that I wanted to put X is equal to GZ. So basically your Z is going to be equal to G inverse Z. And in this way, what's going to happen, that wherever the Z's you are having, instead of that, you are going to get X's. Yes, so let us write it again. If I write it again, this thing becomes this thing, this thing becomes this thing, and dz becomes this thing. I write it over here. Please keep it ready.
सर
First term, yes.
सर ये इंटीग्रल लिमिट जो z से x किया है यहाँ x होगा कि g इनवर्स x लिखेंगे?
हाँ, यहाँ पर x लिख ले या g, हाँ, g inverse x basically, yes. So it's going to be now integrated over x. Yeah, so it's going to be now integrated over x. Everything now converted into x. ठीक है?
Yes.
Yes.
Sir, can you scroll above to equation 2?
Equation number 2. Is this the equation number 2?
No, just above it. Okay.
There is some equation number 2 I have written. I don't know that it is it 2 or 1. This is 1. There has to be another 2 equation.
Yes, sir. This
Oh,
one.
this one. Okay, this one is the right.
I don't
Yes.
have a question. Just wanted to note this.
Note that. Okay, fine. Yes. So this is my equation number 2, and then what we have done is that this part B of the discriminator's loss function, part B, we have changed the variable, and variable now got changed into x. Now you see that this thing multiplied by this, what it becomes? This actually become PG. We just have written that. So using the second equation, I am saying that this multiplied by this becomes PGX log of 1 minus dx. By the way, these things I have got from multiple places, so it's not being done by me. Anyways, it is being done in the paper, but not in this much extent. Probably some resources like Ahlad Kumar and others, I have got this stuff. So we will be giving the proper credits to them as well. Not being mathematically formulated by me, don't worry. So it's actually this thing and this thing, both of them are going to be multiplied, and this is actually my PGX using second equation. So this becomes this, and this value is actually coming over here, and this is the x, which is going to be there. Along with this, so now what you can see? Now what you can see is that this is only B part. Where is my A part? This was my A part. This is my B part now. So finally, my loss function Vg comma D that I wanted to maximize when I was trying to maximize my D, when I was trying to maximize the loss for my D, this is the complete loss function. And all of them, all of these things are now in X. Please write it again. P data X log of dx. Dx, PGX log of 1 minus dx and dx. All of them are actually having only X variable. And this thing is going to be D asterisk G is going to be the maximization of this term. You want to maximize this guy. Up to this, I assume that all of you are clear. And when you are going to optimize this guy, this is fixed and this is optimal. So this is fixed. And you wanted to, come up with a dx. You wanted to come up with some dx, which is best suited for my g. For a given g, best suited gx. Given this function, how can you maximize it? So all of you can understand that this is the function that you are going to have. Any given function, if you wanted to maximize a function, only one thing that you need to do is that you need to differentiate. And here what you have to differentiate, you have to differentiate this guy with respect to this. Because this is the thing that you want that, I want the best possible this. So this is the parameter that you want. Basically the dx value, best dx value that you are looking for. The best dx value, you can differentiate this with respect to this. And if you can do that, we can see that this is fixed. And the derivative of this with respect to dx is going to be 1 by dx. That's coming over here. And similarly, pgx and 1 divided by dx. And this thing is being equal to 0 for the maximization. And once you solve this thing, please keep on solving. So very easily you can solve. And once you solve, you are going to get D asterisk. So now whatever the D that you are going to get, that is the maximal D asterisk X that you are going to get, which is going to be equal to this. Very easily you can prove now. So practically you cannot estimate this because it's actually a very big distribution. And we also have seen in the case of VAEs, we were not in a position to really prove it. But practically we cannot prove, but theoretically or analytically, if I say that it's being shown that if you train it in such a way so that your optimal, for a given G, the optimal D is going to be equivalent to this. We are going to use this to prove the second part, that is the essential and the crucial part. I assume that was simple. The second part is even simpler than this. Now the role of a generator is reverse of D. You have got an optimal D, generator's role is reverse. Hence, for the best optimally chosen discriminator, we need to obtain an optimal generator. How to get an optimal generator for the optimal discriminator? And this is going to be the specifically minimization of all possible G's. We need to minimize for all possible G's what is the for a given discriminator. For a given best possible discriminator, we need to minimize all possible G's, and then you are going to get the best one. How we are going to get? Let me write it again. Your G asterisk is going to be argument minimization for this G. All possible G's, I wanted to minimize it in such a way so that this and this. Here you see that what we have used the discriminator, and not only the discriminator, we are using the best optimal discriminator. Is this part clear to everyone? Or if it is not, then you can ask again to me. In 5 to 8 minutes, we can finish. So please be with me. Don't worry, slightly heavy, but I am assuming that it was not very difficult. All of you probably able to understand it in the best possible way. Anyone is having any question or any doubt here, please ask why I have written this. Richa Thakur, are you there?
Yes, sir.
Do you have any doubt over here?
No, sir.
No, sir. Divyansh is there?
Yes, sir. Yes, sir.
Do you have any doubt over here?
No, sir.
No doubt. Good. Okay. So this is, I assume that it's going to be a simple thing. And what you need to do is that if I take this best possible D asterisk G, what is going to happen? So we need to minimize this. Okay. What we are going to do is that very simple trick that we are going to use. First of all, instead of this, I am going to use this. I assume that we are not going to have any problem like this because this is the best possible discriminator's output. Best possible discriminator's output is going to be things over here. Best possible discriminator's output is coming over here. We have shown it previously. So P data, so you please write it again. It's a repetition 3 to 4 times. Keep on writing very fast. I'm giving you time. I'm reading. Argument for all G's, integrate X, P data X, log of P data X divided by P data X plus PG. That is coming directly from my previous proof, plus that is PG, the generator distribution, multiplied by the log of PG. Here it was PD, here it is PG. Why? Because that was 1 minus D asterisk G of X. This thing, sorry, not G of this thing. Real thing. So what you are going to get over here is that PG, here it is P data and here it is PG, because this is 1 minus of this. Yes. Along with that, so this is going to be the arg minimization of this whole thing, the big term which is actually being written. I'm playing a small trick. I'm adding and subtracting two things. Log 2 P data X minus log 2 p data x plus log 2 pgx minus log 2 pgx. In this whole term, in such a big term, I have added this and subtracted this. I have added this and subtracted this, so that this and this got cancelled, this and this got cancelled. This remains to be the same. I have not done anything. You just add both of them. I will add both of them and I will absorb this thing to first term and PG thing to this term. Understood? So what I am doing is that I am adding these two because these are the two negative terms. Both of them are going to be here minus log 2 and PG and P data. They got added. Okay. Plus now the first term. Now you see that this thing and this thing, if they got added, wait. What I was doing? Yes. So if you take this and if you take this, what is going to happen is that p data x got common, and this is log 2, and it's here. They are going to be added, so log 2 comes in. Similarly, pgx and pgx become common, and this becomes log of this plus log of 2, so 2 will come inside. Here it will become 2 multiplied by this. Same thing, p data pg log 2 p data by p data plus pg, and this is 2 times pgx p data by this. Now if I show, yes.
So ये जो last step है जिसमें आपने ये log 2 वाली equations लिखी हैं,
yes,
ये कहाँ से आई?
ये तो बस मैंने, आप ये जो ये रंग में जो लिखा हुआ है इसकी बात कर रही हैं?
हाँ जी।
ये मैंने जोड़ दिया और घटा दिया, मैंने कुछ तो काम किया
अच्छा,
नहीं यहाँ। ठीक है
हाँ
ना?
जी,
वो वही का वही रहा। ठीक है, ओके। मेरे ख्याल से कुछ लोग यहाँ फंसे होंगे, इसलिए मैंने बार बार बताया कि यहाँ तक मैंने प्रूफ करता था, लिखा था कि हम इसे मिनिमाइज कर रहे हैं, इसी में कुछ जोड़ दिया घटा दिया, कुछ जोड़ दिया घटा दिया, कोई फर्क पड़ेगा नहीं, वो वैसे का वैसे ही रहा। एंड हमने इन दोनों को एक साथ में ले लिया, इन दोनों को एक साथ में ले लिया, इसको मैंने पी डेटा टर्म के साथ लिया, इसको मैंने पीजी टर्म के साथ लिया। तो अगर आप ध्यान दें तो दिस बिकम्स माइनस लॉग ऑफ 2 पी डेटा प्लस पीजी प्लस this will become p data log 2 times p data plus pg, and pg log 2 times pg and p data. See, some important thing is coming. I need to take a call. Wait, hello. लेकिन मैं आपको ना क्लास चल रही है मेरी, इसके बाद आपको फोन करता हूँ। हाँ जी। Yes, so yes, so we have got pg 2 times this, keep on multiplying, right? This is very easy. Now the thing is that if this is an integral and this is a distribution, and if this got integrated, you are going to get 1 here. Any probability distribution integrated, you are going to get 1 over here. This is also going to give you 1 over here. Integral of pgx is equal to the integral of pg theta, which is going to be equal to 1. So here you will get 1 plus 1, and this whole thing, this whole integral is going to give you 1 plus 1, which is actually going to be equal to 2 log 2, that's log of 4, and negative log of 4. By seeing this, probably you may not be very happy that what you have got and why I have done this all, arbitrary steps. Soon you will be able to understand that if I say that this is actually nothing but the JSD between PG and P data. Why? Because PG and P data And this is what? P data divided by PG, P data by 2. This thing is coming over here. And that was my M. So this is PG. So this is this is going to be the KL between P data and PM, and this is going to be the KL between PG and PM, addition of both of them. So that is why what we have done is that my G stick is going to be this plus this plus this, and which is essentially equal to the same thing. Again, I have written the same things. I'm writing multiple times, don't worry. That's actually my log of minus log of 4. And this is nothing but the GST between them. That's why it's being written. It's a 2 times GST because 1 by 2 something has happened. It becomes 2 times of GST between P data and PG. That is my minus log of 4. That is arc mean for you. This shows that optimization to get this GST is actually equivalent to GSD minimization between PG and P data. This is first thing that we wanted to show. And the second thing is that if you minimize the GSD between them, your GSD is going to be equal to 0 at some point of time when it's going to converge, or not maybe 0, they are going to be very close to each other. So PG and P data, they are going to be very close, which means that if your GSD reaches to 0, your generated distribution is getting close and close to P data, and your V distribution, this loss function is actually going towards minus log of 4. So once you understand these things, as simple, straightforward things, this shows that the global minima of the criterion function this is achieved if your PG and P data are very close, and the loss is going to be minus log of 4. We just have shown all these things. I am writing over here again. And the goal of your GAN is to generate the optimal GST is being done effectively by minimizing the GSD between P data and PG, we just have shown. And it's going to be converged when PG and P data, they are same. And the corresponding discriminator is going to be, if you all remember, that was P data divided by P data plus PG. And if both of them are same, it is going to be half. So the best output that you are going to get from a discriminator when your generator is well trained, it's going to be half. It's going to be no better than a random coin toss. The output of a discriminator is going to be no better than the random coin toss. That's why it becomes equal to half. We're going to stop over here, and too many things I've covered. Maybe what you can do is that I will upload these slides probably, and lecture is also going to be uploaded. If it is not going to upload it soon, you can check this lecture out on my previous year's website, because exactly same things I have covered over there. Whatever you have written, keep on writing it 1 or 2 times so as to adjust and come up with any other issues or the concerns that you have, or if you have any question, then you can ask that in the next lecture when we are going to start our class. Thank you. So in next lecture, we are going to see a few more problems with GANs. Thank you. We are done. How many were there? 23, 22. Okay. Leave.